Hi everyone. This is Dr. S. Venkateswarlu, working as a professor of EC at IARE Hyderabad. Today topic is PLL. Phase lock loop. The phase lock loop, the introduction to the PLL, phase lock loop. Here, the concept of PLL first emerged in the early 1930s. But the technology was not developed as it is now. So the cost factor for developing this technology was very high. Since the advancement in the field of integrated circuit ICs, so this is one of the main building blocks in the electronic technology. The present, the PLL is available as a single IC in the SE NE560 series. So normally 560, IC number 560, 561, 562, 564, 565 and 567. To further reduce the buying this cost, so the discrete ICs are used to construct a PLL, phase lock loop. The phase lock loop PLL is an important building block of linear systems. Electronic phase lock loop came into the in the 1930s when it was used radar synchronization and communication applications. Now with the advanced IC technology, phase lock loop are available as inexpensive monolithic IC, like a single store ICs. This technique for electronic frequency control is used today in satellite communication systems, airborne navigational systems, FM communication system. Nowadays, that's all communications are going on, and the computers and so on. The basic principle of PLL, different ICs and important applications are discussed as per this. Due to this whole scenario, the advanced IC technologies PLL are available as inexpensive monolithic ICs. So that the basic principle of PLL, different ICs and important applications we will discuss. Basic principles, the basic block diagram or block schematic of the PLL is observed. This due to this all block diagram, the feedback system consists of phase detector or comparator they are using, and low pass filters they required, error amplifier and voltage control oscillator VCO. The VCO is the free running multivibrator and operates at a set frequency F0 called free running frequency, where it is set at F0, where F0 is the free running frequency. This frequency is determined by an external timing capacitor and an external resistor. It can also be shifted to either side by applying a DC control voltage PC to appropriate terminal of the ICs. So this, the frequency deviation is directly proportional to the DC control voltage, and hence it is called a voltage control oscillator. Now we can consider VCO. In short, VCO. Now consider this block diagram. PLL, phase lock loop block diagram, where in input section, input signal is given to that phase detector. That input is Vin or F1. Okay, the output of this phase detector is given to low pass filter. Here it is, that output is low pass filter output is, that the functionality of low pass filter, like it is, it allows only low frequency components, it opposes high frequency components. You know that output response is given to that VCO, voltage control oscillator. In between that there is observed in between the phase detector and voltage control oscillator. So forward path is observed here. So that VCO output is outcome is given to that F0. Observe that F0 output signal will be appeared. The F0 is connected with what you call phase detector. Okay, PLL block diagram. The block diagram of the basic PLL is shown in the above figure. It is basically flip-flop consisting of the phase detector, a low pass filter, and a voltage control oscillator. Okay, the voltage control oscillator, PLL, the input signal Vin with an input frequency of I is passed to a phase. Okay, phase detector, basically the comparator which compares the input frequency of I, with the feedback frequency of naught. Yeah, the frequency, the F naught is the feed for path, disconnected F naught and V naught. Okay, the phase detector provides an output error voltage. Okay, so where VR is equal to Fi plus F naught, where VR Fi plus F naught. Okay, which is a DC voltage. Okay, this DC voltage is then passed on to a low pass filter. Here it is given to that all DC DT voltage is given to that here, given to that low pass filter. Okay, now the low pass filter removes the high frequency noise or components and produces a steady DC level. Okay, so the time that VF is observed here, where VF is equal to what you call, so Fi and what you call Fi minus F naught, where VF also represents the dynamic characteristics of the PLL phase loop. The DC level is then passed on to a voltage control oscillator. Yeah, the output frequency of the VCO is followed by F0 as per the previous block diagram is directly proportional to the input signal. Both the input frequency and output frequency are compared and adjusted to feedback loops until the output frequency equals the input frequency. Thus, the PLL works in these stages: free running, capture, and phase lock. As the name suggests, what you call free running stage refers to the stage when there is no input voltage applied. Okay, so within this, as soon as the input frequency is applied to the VCO, it starts to change and begin producing an output frequency for comparison. This stage is called the capture stage. The frequency comparison stops as soon as the output frequency is adjusted to become equal to the what you call the input frequency. Yeah, this stage is called the phase locked stage. Okay, so now the stage is observed. This is called phase locked state. Now let us study the detail about this, how it is appeared, various parts of the PLL, the phase detector, low pass filter, and voltage control oscillator. In depth of that. Okay. Coming to this first one is phase detector. This comparator, this is nothing but comparator because of the phase detector. This comparator circuit compare the input frequency and the VC voltage controls oscillator output frequency and produces the DC voltage that is proportional to the phase difference between the two frequencies. The phase detector used in the PLL may be of analog or analog type or maybe digital type. Even though most of the monolithic PL phase lock lobe integrated circuits or IC use analog phase detectors. Yeah, the majority of the discrete phase detectors are of the digital type. Okay, one of the most commonly used analog phase detector is the double balanced mixer circuit. Some of the common digital type phase detectors are what do you call exclusive OR phase detector. That means they are using an exclusive OR phase detector is usually can observe that by using the block diagram. Usually can understand that one. Okay, here it is. This is the exclusive OR phase detector. So they are using the exclusive OR gate. So two input exclusive OR gate Fi and F0 VDC is observed where it is Fi and F0 is observed the output. If Fi is low, F0 is low, what do you call slow? That means here it is 0 0. Okay, here it is 0 1. Here it is 1 0 and 1 1. Then here low. If it is Fi is low, F0 is low, output is low. If F1 is low, F0 is high, output is high. If it is Fi is high, where F0 is high, output is low. Okay, like this, it is obtained as a CMOS IC of type 4070. Both the frequencies are provided as an input to the exclusive OR phase detector. Okay, obeying the exclusive OR concept, of course, the output becomes high only if either of the input Fi or F0 becomes high. All other conditions will produce a low output. So let us consider the waveform where the input frequency leads the output frequency by theta degrees. That is Fi and F0 as a phase difference of theta degrees. Okay. Yeah, the DC output voltage of the comparator will be function of the phase difference between its two inputs. So, as per this block diagram, shows the graph of DC output voltage as the function of the phase difference between Fi and F0. Okay, the output DC voltage is maximum when the phase detector is 180 degrees. Okay, yeah, this type of phase detector uses what you call when the both Fi and F0 are square waves. Okay, within this here we can observe this one here exclusive OR phase detector waveform. Here it is okay. Due to this all you can observe that all output response. Coming to the next edge triggering phase detector. Edge triggered phase detector is used when when all are involved with what do you call Fi and F0, isn't it? If it is edge triggered pulse detector is used when Fi and F0 are pulse waveforms with less than 50% duty cycle. Based on this duty cycle, the figure of such a phase detector using an RS flip-flop. Okay, we'll observe that using the block diagram. Two NOR gates, it is followed by CD4001 are cross coupled to form an RS flip-flop. The output of the phase detector changes its logic state by what you call triggering of the RS flip-flop. That is, the output of the phase detector changes its logic state on the positive edge of the input input data of the F5 and the F0. Okay, like this, the advantage of such a detector can be understood from the graph or graphical representation. It's clear that the DC output voltage is linear or non-linear, linear over maybe 360 degrees or other degrees. Okay, like this, monolithic phase detectors. In monolithic phase detector, the monolithic type phase detector uses CMOS type 4044 IC, which is highly advantaged as the harmonic sensitivity and the duty cycle problem are neglected. Okay. Okay. So, and the circuit will be respond only to the transition in the input signal. Yeah, this is the most preferred phase detector in the what you call critical application, as the phase error and the output error voltage are independent of variations in the what you call amplitude and duty cycle. Due to that amplitude and due to this amplitude and duty cycle of the input waveforms. Okay, like this. Next, low pass filter. Yeah, that PLL internal block diagram, functional block diagram involved this all VCO and low pass filter and so on. Now we are entering the low pass filter. Low pass filter is used in the phase lock loops to get what you call rid of the high frequency components in the output of the phase detector. Yeah, it also removes the high frequency noise. All these features make the low pass filter a critical part in PLL phase lock loop and helps control the dynamic characteristics of the whole circuit. The dynamic characteristics include capture and lock ranges. Here, the capture and lock ranges, and what you call bandwidth, the transition response. The lock range is the tracking range where the range of the frequencies of the PLL system follows the input frequency. Okay, so the capture range is the range in which the PLL attains the phase lock. When the filter bandwidth is reduced, the response time is increases. Hello? Yeah, this is 100%. But this reduces the capture range, but it also helps in reducing noise. This is another thing. Reduces the noise, reducing the noise. Okay, and then maintaining this locked loop momentary losses of signal. Okay, so two types of the passive filter are used for the low pass circuit in phase lock loop. So one is an amplifier is used also with the low pass filter to obtain the gain. Okay, other one is the active filter used in the PLL is calculated by using the block diagram. Okay, now third one is VCO, voltage control oscillator. The main function of the VCO is to generate an output frequency that is directly proportional to the input voltage. The connection diagram of SE and NE566 VCO is shown in the below figure. The maximum frequency of the VCO is 500 kHz. This VCO provides simultaneous square wave and triangular wave output as a function of the input voltage. Okay, yeah, the frequency of the oscillation is determined by the resistor or and capacitor C along with the voltage Vc applied to the control terminal. Okay, so monolithic phase locked loop. Here in this case, PLL is now readily available as ICs which were developed in the SCNE560 series. Okay, some of the commonly used ones are the SCNE, so 560, 561, 562, 564, 565 and 567. Okay, so the difference between each one of them is in the what you call different parameters. What parameters are involved here? So like operating frequency range, this is the major one. One is operating frequency range, power supply requirement and frequency. Yeah, finally that bandwidth ranges. Out of this series, the SE 565 is the most famous due to this in the different parameters like operating frequency range, power supply requirements, and frequency and bandwidth ranges. Okay, it is available as a 14 pin DAP dual in package and also as a 10 pin metal can package, which one the PL. But as per our thing, 565 PL. The 14 pin DAP and its characteristics are observed by using this graphically. Monolithic PLL characteristics. So because of this monolithic PLL characteristics, monolithic PLL is available. There's a single stone PLL, like all series and SENN. So we should remember, we should recollect these all characteristics. Monolithic PLL phase loop characteristics. One is operating frequency range is what you call 0.001 Hz to 500 Hz. Operating voltage range plus or minus 6 volts to plus or minus 12 volts. Yeah, input impedance is 10K. Typically, that output sink current is 1 milliampere. Typically, output source current 10 milliampere. Typically, okay. Drift in VCO center frequency with the temperature is 300 ppm per degree centigrade. Typically, okay. Drift in VCO center frequency with the supply voltage is 1.5% per V maximum. Okay. Next characteristics, input level requirement for the tracking 10 milliVRMS, minimum to what do you call maximum is 3 volts peak to peak maximum. Okay. And bandwidth adjustment range is less than plus or minus 1 to greater than plus or minus 60%. So the range, bandwidth range. Okay. Like this, these are the monolithic PLL characteristics. Now the block diagram and what do you call connected the block diagram consists of here. It is available. The block diagram here is lock loop. External and difference with the help of this. So how many pins are available here? Okay, here pin out diagram. Based on this, the block diagram, it consists of the phase detector which acts as the phase comparator, an amplifier and low pass filter with the combination of the resistor 3.6 kilo ohm and capacitor C2. The output of the amplifier is fed back to the voltage control oscillator. Yeah, the different pins represented of the IC are also shown in the block diagram. Pin number 1 and 10 are the positive and the negative supply pins. The pins 2 and 3 are the input to the phase detector. Okay, the pin 2 and 3 are the input of the phase detector. The input signal are fed to these pins in what you call different mode. Pin number 4 is the VCO output and pin 5 is the phase comparator DC input. With both these pins are shorted, the output of the VCO is supplied back to the phase comparator. The output of the phase comparator is given to the amplifier. The amplifier has 2 outputs that goes to the external pins as the demodulator output pin number 7 and the reference output pin 6. A low pass filter circuit is formed by the connecting the capacitor C2 between the pin number 7 and 10 with the resistor of values 3.6 kilo ohm. The value of C2 must be large enough to eliminate the variation in the demodulated output and stabilize the VCO frequency, voltage control oscillator frequency. Okay, like this. Pin number 8 and 9 are used to connect the external resistor R1 and the external capacitor C1. The values of the R1 and the C1 helps to adjust the free running frequency FR and the phase lock loop. So the value of the C1 can be anything. The value of resistor R1 must have a value between 2 to 20 kilo ohms. Yeah, all these factors can use to determine the center frequency of the PLL phase lock loop. The free running frequency of the PLL is given. FR is equal to 1.2 by 4 R1 C1. The lock range of the PLL is given as F lock. It is followed by F lock is equal to plus or minus 8 FR by V. The capacitor range of the PLL is given. It is followed by FC. Okay, where F lock by 2 into 3 into C2 into 1 by 2. The lock range usually increases with an increase in the input voltage, but falls with an increasing in the supply voltage. Okay, like this. I have to verify. Phase lock loop is a negative feedback system in which the frequency of an internal oscillator VCO is matched to the frequency of the external waveform with some predefined phase difference. You can show here the block diagram. Phase phase comparator PC. Here input is V in of T is given to the phase comparator PC. Okay, so the phase comparator PC is given to that low pass filter VP of T. The low pass filter output is connected to the amplifier A. Output of this amplifier A, it is given to that VCO, that K0 is equal to VCO into del F by del V. It is an external or RNC determines the VCO frequencies. Now it is output of this VCO, it is connected with PC, and you have to verify that because of V0, that input is Vi of T. Using this all scenario, it is given to that that PC. PC is connected to the low pass filter, isn't it? The low pass filter is output is connected to the amplifier. Output amplifier is connected to K0, and finally we are going to verify that V0 of T final output. Okay, so phase lock loop, phase comparator. The phase comparator, or we can consider the phase detector, can be as simple as an exclusive or gate, digital signals, or it is a mixer, or we can consider non-linear device, frequency multiplier, or analog signals. This game, the phase comparator generates an output voltage. Okay, P of T relates that to the phase difference between the external signal V1 of T and the VCO output V0 of T. These are the external signal. Because of using this block diagram, you can observe that our external signal V1 of T and VT of T. The two frequencies are the same, with free defined phase difference, then V0 of T equal to 0. The two frequencies are not equal with various phase differences, then Vp of T not equal to 0. So basically we have the two conditions, Vp of T is equal to 0, Vp of T equal to not equal to 0. And with the frequency components, so about twice the frequency, input frequency. Okay, now come to the low pass filter. We know that low pass filter. The low pass filter removes this high frequency components, and Vd of T is a variable DC voltage, which is a function of the phase difference. Now coming to the VCO, voltage control oscillator. The VCO has a free running frequency followed by F0 approximately equal to the input frequency. The VCO frequency varies with the function of Vd of t. Okay, the feedback loop tries to adjust the VCO frequency so that V of t frequency is equal to V naught of t frequency. So the VCO, voltage control oscillator, is synchronized or locked to V1 of t. Okay, that means here it is V1 of t is equal to V2 of t. The voltage control oscillator is synchronized or locked to V1 of t. Okay, lock range. So that means here in PLL, phase lock loop lock ranges. Basically, we are having the two lock ranges. One is lock range and hold in range. First one, lock range. Lock range is defined as the range of the frequencies in the vicinity of the VCO natural frequency, free running frequency, for which the PLL can maintain lock with the input signal. The lock range is also called as the tracking range. The lock range is a function of the transfer functions of the PC, okay, amplifier and VCO. The next one, hold in range. The hold in range is equal to half the lock range. The lowest frequency that the PLL will track is called the low lock. Yeah, there is a limitation using this one. The highest frequency that the PLL will track is called the upper lock limit. Okay, like this, that the PLL lock range is observed. Okay, the PLL lock range here, the upper lock limit and lower lock limit, the hold in range, it is followed by F1, and hold range and the lock range is equal to 2F1 because of hold in range 1, F1 and F2. So is a PLL lock, phase lock loop lock range is try to observe like this. Low, upper lock limit and the lower lock limit. So these are okay. This hold in range, here is hold in range because of the whole thing is lock range is equal to 2F1. Now PLL capture range, capture range and the full in range. Okay, the capture range is defined as the band of the frequencies in the vicinity of the F0 where the PLL can establish or acquire lock with an input range also called the acquisition range. Okay, the capture range is the function of the bandwidth of the bandwidth of the low pass filter. Okay, yeah, it is reduces the bandwidth of the capture. Okay, the capture range is between 1.1 and 1.7 times the natural frequency of the voltage control oscillator. Yeah, coming to this, the full in range. The full in range is equal to half the capture range. The lowest frequency that the PLL phase lock loop can lock onto is called the lower capture limit. Like this, phase lock loop capture range is observed. PLL capture range. The highest frequency that the PLL can lock onto is called upper capture limit. Capture range is equal to into FC because of full in range is the FC and full in range is the FC. So you can observe that one here. Okay, from here to upper capture limit and lower capture limit. PL lock, capture lock. Yeah. So they are combining the both PLL lock range, phase lock loop lock and the capture range. Okay. So they are combining that the FC1 and FC1 and FCU and FN versus F. Okay. This is the PLL lock and capture range. Yeah, PLL basic components. Phase detector, phase function is, transfer function is K pi radians implemented as 4 quarter multiplier or exclusive state gate state mission phase detector. Coming to this voltage control oscillator, frequency is the first what you call derivative of the phase transfer function, and in terms of the radius for what into t like this here by one of these phase comparator kp, and the input is this one like it is connected. Okay, VCO. Okay, VCO and together like this. So this is the phase detector and VCO. Yeah, in terms of the low pass filter, removes the high frequency components coming from the phase detector, determines the loop order and the loop dynamics. VP of S is given to the F of S. Output will write to verify the V of S. Like this, with help of the FS. Next, phase lock loop. About the working of PLL phase lock loop. Let us consider the free running frequency to be FR. Let FR be the frequency at which VCO is running without input signal. Okay. Let the input signal, if the increasing the from 0 to applied the phase comparator. Okay. The graph between the error voltage and the input frequency is ready to observe. It can be seen that when the input frequency is lesser than F1, Fi1, the error voltage ER is reduced to 0. At this time, the VCO will operate at the free running frequency FR. When the input frequency, when the input frequency Fi increases, where here it is, Fi increases, okay, and it reaches what you call Fi1. The error voltage jumps from the 0 to a negative voltage. This value will be equal to the difference between the input frequency and the actual whatever VCO output frequency Fi minus F0. This resulting error voltage is then processed by filtering, amplifying, and applying the amplified voltage. It is followed by VD to the control terminal of the voltage control oscillator. Like this, we are to observe this on phase lock loop working principle. Okay. Now, the instantaneous frequency of the VCO decreases because of the falls of the negative values of VD and increases the positive value of DRF at some instant of the time. Decreasing frequency of the VCO equal to F in 1. So you have to consider the lower edge of the capture range. The lock result in and output signal frequency of the voltage control oscillator may be equal to the input signal from the, that is F0 is equal to what we call F5. Okay. The VCO frequency locks with the input signal frequency up to Fi2, that is the upper end of the lock range. The input signal frequency exceeds Fi2, then error voltage Vg will fall to 0. Okay, and the VCO voltage control oscillator will operate at the free running frequency Fr. As illustrated, if the input signal frequency is now slowly swept to the back and returned to the value of what you call Ft1, okay, and then the loop VCO frequency looks the input signal frequency with the input signal frequency causing the positive jump of the what you call that voltage. Okay, the VCO when the continuous still becomes equal to F. The VCO voltage control oscillator frequency F0 locks with the input signal frequency F1 up to FD2. That means lower edge of the lock range. As per figure it is mentioned, Now if the frequency of the input signal falls below FD2, then the error voltage VER will fall to 0 and the voltage control oscillator will operate at the free running frequency. Using this all scenario, the description, the interpretation, the voltage controlled oscillator will operate at the free running frequency. Okay, like this, PLL operation putting all together here. So mathematically is observed. External input signal using the phase comparator and Q0 and what you call low pass filter. In terms of this, all mathematical notations are involved. VD is also calculated there. V0 is also calculated. That is also calculated. Is calculated using the PLL operation, putting all together with this. User can refer finding that what you call V0. If the K0 is equal to del F by del V, K0 del F by V output, where that V output is equal to del F by K0. So if you want that del F, where del F is equal to V0 into this one. Yeah, here it is cross multiply this one, here and this one. Like here, del F is like this. V0, V out into K0. Del F is equal to Fn minus F in minus Fn. Like this, all together, all PLL operation putting all together is conjunct all output response with the gain, external input voltage and phase errors, everything is observed based on this single bit. Yeah, the PLL operation hold in range here. VD is maximum, theta E maximum KD into is equal to plus or minus pi by 2 into KD. Here it is observed here. Plus or minus del F maximum plus or minus pi by 2 KD into KF, KA, K0. So finally it is plus or minus pi by 2 into KM. The lock range is equal to 2 del F maximum pi into KL. Okay, like this PLL 565 pin-out diagram. Yeah, this is the pin-out diagram. Already we have seen that pin-out diagram. How many pins are available here? 14 pin. Already we have seen that 14 pin dual in package. NESC 565 pin-out diagram. That's the pin-out. Click on the pin-out diagram. This is the block diagram of IC 565. PLL block diagram to determine lock range. By using this simple block diagram, user can calculate the lock range. Okay, using the block function block diagram, IC 565. That is phase detector is connected with this second pin and third pin is both are input. So fifth pin is connected to the phase comparator VCO input. Fourth pin is connected VCO output. Fifth pin is and fourth pin is connected to VCO with the 8th and 9th pin. First pin is connected that is 9th pin with the help of C1 capacitor 1. Yeah, like this in amplifier is connected with what you call 7th pin. Okay, and the 6th pin is connected to the reference output and so on. This is the PL 565 pin configuration. With the first pin is minus V, second pin input, and what you call third pin is input, and fourth pin is VC output, and fifth pin is phase comparator. Sixth pin is what you call reference output. Okay, and seventh pin is what you call demodulated output, demodulated input, and eighth pin is external resistor for VCO. Ninth pin is external capacitor for VCO. 10th pin is plus V, 11th pin no connection, 12th pin is also no connection, 13th pin also no connection. These are all NC, not connected, no connection. So here, so you will see the simple problem on this. Like problem is followed by Fn is equal to 200 kilohertz, Fi is equal to 210 kilohertz, and what do you call KD is equal to 0.2 volts per radian. kf is equal to 1, k is equal to 5, k naught is equal to 20 kilohertz by volt. Okay, now we are calculating this consider open loop. Okay, there we want to calculate the KL. So calculate the KL and VCO frequency range for lock or phase lock loop output voltage with the help of the given specification. So we are calculating the open loop gain. Open loop gain, the KL is equal to, here it is, VCO frequency range for lock, del F is equal to Fin minus Fn. Fn is given. Okay, Fn is given now, where Fn is recall 210 or Fn is also given 200, 210 minus 200, it is equal to 10 kilohertz. That is the VCO frequency change for lock del F. Okay, now PLL output voltage. PLL output voltage, the formula is V output is equal to del F. What do you call del F by K naught? Del F is given, K naught is also given. 10 kilohertz by 20 kilohertz by ohm, it's 0.5 volts. Like this, we need to calculate. If some parameters are not given, if they are given Fn and Kd, sometimes they are not, it is not provided with Kd and Kf, K naught value, supposed to have to calculate this remaining parameter. So using with help of the VCO frequency range and lock range or PLL output voltages. The next PLL example here, phase detector output voltage Vd equal to V output by Kf into K, like this. Static phase detector, vertical error. So you should follow this typical value and hold in range. Yeah, it is available plus or minus 31.4 kilohertz. And lock range, consider that all some practical manner they are calculated, they measured the typical values. Silent features of 565 PLL phase lock loop. What are the silent features? Like operating frequency range is 0.01 Hz to 500 Hz. Operating voltage range is plus or minus 6 volts to plus or minus 12 volts. Input level required for the tracking 10 millivolts RMS minimum to 3 volts peak to peak maximum. Input resistance 10 kilo ohm typically. Output sink current is 1 milliampere typically. Output source current 10 milliampere. And drift in voltage control oscillator center frequency 300 ppm per degree. See, drift in VCO center frequency with the supply voltage 1.5 percentage per V maximum. Like this, square wave amplitude and bandwidth adjustment and triangular wave amplitudes, so all typical values are available. These are the silent features of 565 PLL phase lock loop. PLL applications. Analog and digital modulation. That purpose we require the PLL, frequency shift keying decoder, AM modulation and demodulation. Okay, and FM modulation, demodulation, frequency synthesis, frequency generation. Okay, so these are the major applications. Like this, you are ready to observe this PLL phase lock loop is very much useful in what you call communications, like analog communication, digital communication, and so on. So, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.